The next talk today is about the AMD Instinct Accelerators and the ROCm platform. Over to Michael and Derek for this talk.
All right, thank you. Thanks for having us. So I'm Michael Clem. I'm a principal member of technical staff in AMD's HPC Center of Excellence. I'm working on all sorts of GPU related questions, especially when it involves application porting and the software ecosystem. And I have with me Derek Boyus, who's a senior product manager and kind of a counterpart of myself in the GPU computing software team, managing the GPU products in terms of software. The usual cautionary statement, I'll just quickly let it pass by so that people can watch it on the recording. The agenda that we want to go through today is I'm going to introduce the AMD Instinct Architecture. I will give you a little bit of an overview of how the GPU looks like and how it's working. And then Derek will take over talking about the software piece of the equation, the ROCm software stack. That's the drivers, the runtime libraries, the math libraries and everything. And then he's also going to touch on the software ecosystem. And in the end, we're going to have a little more than 10 minutes, hopefully, for Q&A and interactive session about questions and answers and feedback and whatever you want to discuss. All right, so let me start with the Instinct architecture. So, this is kind of a historic perspective on what happened in a few decades of HPC and leadership computing. So in the early days, let me call this the terascale era, it happens to be so that CPU only was the main and prevalent architecture that you would find in those systems. So, there are a bunch of poster child example like the ASCII White system, which I believe was the first one to cross 1 teraflop. The Great Jaguar was one of the later systems. And then there was a transition in how these systems were built and how they were designed. And that is when the petascale era started. And it happened that GPU accelerated computing became more prevalent in those systems. And the systems itself, the node level design, was moving away from homogeneous processors to heterogeneous systems that were using processors to drive the workload and have GPUs on top of that to deliver the floating point, the number crunch performance, if you will. There were still some CPU-based systems here and there, but there was a clear path towards that the high-end leadership systems would be GPU accelerated. And as we are now transitioning into the exascale era, this trend of GPU accelerated computing continues, but now with changes in how the GPUs are working. And actually calling them GPUs, so graphics processing units, is no longer very accurate. They should rather be called HPC accelerators because they are now really geared towards accelerating HPC, or for that matter, also machine learning workloads, and are optimized architectures for that purpose. But still, they carry forward with this idea of having a CPU plus a GPU that accelerates the workload. And so what we did as part of this transition from petascale to exascale at AMD was we basically split the GPU product line into two different separate product lines. So we basically appreciated that, if you build a general purpose architecture that serves both the graphics side of things, so, a domain and regime that is dominated by frames per second and how well you can draw pictures on a screen, versus the HPC regime where you talk more about the amount of flops or the memory bandwidth that you can have in the system. So, you can build a general purpose architecture that serves both kind of well, but you could also make a decision and kind of specialize your architectures into one that is optimized for HPC and one that is optimized for gaming or actual visualization. And so this is what we did at AMD with the Instinct architecture. It is now based on CNDA. That's the compute architecture that we use for our GPUs. And we separated out the Radeon product line that is now then the client and a high-end graphics market. As an example, you have heard about these systems before. So Frontier is almost complete as far as I know. It's the kind of the first system that uses AMD GPUs at a massive scale. El Capitan will also be based on a similar AMD GPU-based technologies. And then there's a whole bunch of smaller systems that are being deployed as we speak and talk about this topic. Lumi is probably one of the biggest ones in Europe. And then, Australia, for instance, the Parsi Supercomputing Center also has an AMD GPU-based system of larger scale. So, it's now being deployed. Let me show you how the current generation AMD Instinct Mi200 series looks like, and we're going to go a little deeper into the technology in like a minute. So this is kind of how the GPU die or the CPU the GPU package is made up. So you can see up here that's the actual CNDA dies. We actually have two of them. So if you think about an MI200 high-end GPU, what you get per package is actually two GPUs. The two dies are connected with Infinity Fabric so that they can talk to each other. We also do have a coherent CPU to GPU interconnect. That means the GPU can directly access the main memory of the host system, and the host system can directly access the GPU memory. And there's a coherence protocol that makes sure the data stays in sync as data is traveling back and forth. There are up to 8 stacks of HBM so that you get a nice multi-terabyte per second bandwidth into from the HBM into the compute dies. And the compute dies itself, they roughly look like this. So consider this a floor plan. It's actually Mi100, but the Mi200 design is very much similar to that. So basically, you can see the attached HBM modules, the memory controllers, and even though I said this is no longer a GPU in the traditional sense for graphics, there are still some concepts showing up, like the main control unit is still called the shader engine, even though there are no longer shader engines or shader units in the whole design. Then we have the PCI Express ports that connect, in this case, the GPU using PCI Express to the host system. And then there's a whole bunch of Infinity Fabric ports that we use to interconnect, in this case, several of those Mi100 GPUs, and a similar design is also used for Mi200. And then in between, there is a whole bunch of those compute units in Mi200. It's 210. So these are the units that do the actual execution. So these are the floating point units, the integer units, and everything that we need to make the GPU fly and do something useful for the program. Each of those compute units roughly looks like this. So there's caches involved and everything that you typically would expect from a GPU. But the way the GPU actually works is that it is actually a SIMD device, right? So the scheduling granularity, when you look at this from the outside in, so in HIP or in OpenMP, the scheduling granularity is called a wavefront. So that's a 64 wide entity of data elements or compute that you can hand over to one of those compute units. Internally, these 64 wide wavefronts are then split into 4 packages, and each of those 4 packages is then a 16 wide SIMD operation that is then executed by this compute unit. So basically, you can think of this as taking the wavefront, splitting it up into SIMD instructions, and then every clock cycle, we're going to schedule one of those 4 16-wide SIMD operations. We do have registers naturally. There are 256 vector registers. You can use 256 of those maximum per wavefront. And then there are 800 scalar general purpose registers where you can use 102 per wavefront. So the VGPRs, these are the ones that contain the floating point data or the integer data that is then used for the processing of the wavefront, and the scalar registers are used for address calculations, constants, and anything that does not fit one of those VGPRs. All right, I already said that we do have a whole bunch of interconnects. So this is one design how you can build a node with 8 GPUs in an HPC system. So you have 2 of those EPYC processors to run the operating system and the regular multi-threading. Each of them is then connected to the one of 4 GPUs. In this case, it's MI100, but we also have the same design for MI210. And now this block of 4 GPUs, they can form what AMD calls a hive. So this is a tightly coupled, fully connected cluster of GPUs, where the Infinity Fabric links that I already talked about are connecting each of the GPUs to each other, so that this block of 4 GPUs can talk to each other quite efficiently. And we can replicate that on the other CPU socket as well. And on the right-hand side, you actually see how this is implemented. So these are the regular PCI Express form factor GPUs. And then there's this additional XGMI bridge that sits on top of them and connects all those GPUs together. And going forward with MI200, you can see that the design is simpler. It's just, if you allow me to say that in that way, bigger and better. So we still have the host CPU for the host threading. And then we have now in this case, this is the coherent design. The blue links up here, these are the ones that connect the CPU and its memory coherently to the GPU HPM controllers. And then we have this additional crosslinks between the individual GPUs, so that each of those dual dies can talk to each other. And then within one of those dual dies, each die also is connected with the appropriate Infinity Fabric links, so that also the GPU dies can talk to each other. And this is then actually effectively a eight-way GPU design. And in this special design, it's even depicted that the fabric is even connected to the GPU directly. On the other side, there's a more traditional MI100 style design where you have the AMD EPYC CPUs, and then you have multiple of those building blocks, again, dual die configuration, but now they connect not using a coherent Infinity Fabric link, but rather PCI Express ports to connect to the host CPUs and its memory, as well as the network interfaces. And with that, I'll hand over to Derek to give you the software story.
Great, thanks, Michael. So just for a bit of background, I've been working with the ROCm software stack for the last 4.5 years, and it's really grown in popularity and experience. And if we move forward to the next slide, we can see that our main goal was to really create an ecosystem for GPU compute that's fully open. And as part of that meant publishing all our source code. So everything's on GitHub. We upstream as much code as we can as possible into other packages, or work with the whole ISV code owners or application code owners to enable the application and have it in the mainline support. So that's worked out quite well. We published the Linux device driver, get that into the kernel, that gets picked up by distros, working with the distro vendors to support the rest of the packages. And I'll go through a little bit more detail in a couple of slides about what specific packages and components that we're working with the ecosystem. But let's dive into what AMD ROCm is. It's really the abstraction of the hardware to the software interface. And as Michael hinted at, there's 2 programming modes that we focus on, HIP and OpenMP. And OpenMP is well known in the CPU world, but you still have to target specific work to run on the accelerator. And so you have this combination between CPU and accelerator to split up the work and then marshal between the 2 components. HIP is the heterogeneous interface for portability. That's a programming mode. It's a C++ base, very similar to CUDA. So if you're familiar with CUDA programming, it looks the same, just with a bit different API. In terms of running host code, you have the compiler and components there that then link the device code where you have a specific kernel that can be optimized and work through the instructions that Michael talked through in each SIMD unit. Next slide, please. So compiling your HIP code, this sort of highlights the methodology that we have HIP-CC that collects all the components as the core. You can compile your host code with other preferred compilers and then link it all together into one package. We also support other devices, and here the example is NVIDIA. So with that same source code, we target the NVIDIA platform with their compiling tools for their target offload. So the host code's still compiled the same, and then you link in the acceleration components for other hardware. The big advantage here is then you have one source code to maintain and support other variants of hardware. There's also been some demos of the new Intel code running. There's public GitHubs on that for supporting level 0. Most of the HIP functionality is supported there now. Next slide, please. So the other way, instead of writing specific kernels, is you can call libraries. And so just as similar as you do in the CPU side, where you're calling BLAS routines, like an SGEM, with a certain set of parameters for performing or passing in the data and receiving the response. And if you just hit next, then you can see that on the GPU side or the accelerator side, you have a little bit more wrapper code to manage to make sure that the data gets transferred across. It knows that it's going to run on the accelerator, but the infrastructure is about the same. So converting from CPU-based acceleration libraries to GPU is very straightforward. Yeah. So maybe the next slide. So going into a little bit more of all the core components of ROCm, these are the parts that AMD spends a lot of time at in terms of optimizing or providing and owning the code base. Starting at the bottom, device driver and runtime, and then the programming models. We talked about OpenMP and HIP a little bit. OpenCL is still supported as well. We see less and less applications using that, but it still has that functionality. Then our compiler environment is all LLVM based. So again, upstreaming that as much as possible into mainline, so that as the LLVM moves along, you get the extra support for the AMD accelerators. We do take all these components, package them and build them, and provide them for the different operating systems. We have Zipify, which is a conversion tool. So that works really well for taking your application that's written in CUDA code, converts it to HIP, and then you can then target both the AMD and NVIDIA devices. So we have lots of examples of that, great success there. And then the suite of libraries really also helps that porting process work easily, where you can convert the code and then link to the AMD implementation that's optimized for BLAS or random number generation, fast Fourier transforms, etc. One call out here is RCL. It's a RCCL, that's a communication library. It's actually the same API as NCL. So if you're using that kind of infrastructure for GPU and node level networking communication, it basically is straight API replacement. You just link that library. And then we have a set of deployment tools that help for managing your device in the cluster. Go to the next slide. We'll talk a little bit more about the ecosystem. So those are the core components that AMD builds. And this is trying to highlight just a collection of some things that we're working with the community in different categories. We'll start on the bottom left. Is deployment and management tools. So I mentioned we have some of those key things for managing on your system, but with Grafana and Prometheus plugins, you can plug it into your existing system. We support the OCI container framework, as well as we have a Kubernetes plugin. So if you're using some of those management tools, they all just work together, and that's all code that's available publicly. On the ML frameworks, we spent a lot of time with machine learning, TensorFlow, PyTorch, working with Microsoft for deep speed, and the Onyx runtime. Those are some acceleration components for PyTorch. JAX is a new library from Google. I have a Docker container for that. And the whole Python community, we're also working with the community to expand generic accelerator support in native Python libraries. In HPC, you have Cocos and Raja as one of the two main projects that are used for offload to support, OpenMP, CUDA for different HIP implementations. It's a really wide abstraction to support the application depending on the hardware. Then we have the scale out. So we support all our components in UCX, and then OpenMPI and MBA Pitch 2 sit on top of that. And I've already talked a little bit about the tool chain, but on the bottom right, let's dive into a little bit more about what we have for EasyBuild. It's in the next slide. So today there's quite a few packages. I went through and grabbed a few to highlight. And I want to just make a special thanks to the contributors that have been looking at this. We have an AMD HPC user forum. This was started by the San Diego supercomputer and a bunch of other customers. And it's a very customer focused group. We meet a couple times a year. And what came out of that was there was a lot of interest in SPAC. And with that SPAC discussion, a lot of interest in EasyBuild. So I want to just say thanks to the contributors for building this out. I know there's a lot of interest in the community in supporting it. Next slide, please. So as part of that container support, we wanted to make it easier for our end users to be able to get applications up and running. So we actually started an Infinity Hub. This is a spot where you can download a pre-built container. Also have some performance results posted there, and invite you to take a look at that. It supports MI50, MI100, and MI200 for most of the components. And the next slide, as part of that Infinity Hub, we've expanded it to link to our learning center. So there's lots of videos, tutorials, hands-on labs that you can work through. Really just trying to make that as the focal point. There's a user forum there as well. And we've also launched the Accelerator Cloud. So this is access to some of the latest hardware in our internal lab. So there's a form you can fill out to request access. And as we go through time, we're trying to just get more people aware and have time on the hardware. So thanks so much for your time today. And I'd like to just say that the AMD Instinct GPUs are seeing some great performance out of them, and really focusing on enabling the open software ecosystem. So let's open it up for Q&A.
Thank you, and we'll pass across to our first person to ask a question.
Hello, you guys are hearing me?
Yes.
Okay. Thank you for the presentation. I have some questions. One is related, I didn't see in the presentation, so I think maybe I know the answer. The OpenACC, it's out of the plans for AMD. And the other thing is that there is, how do you see the support of ROCm in terms of desktop GPUs?
Okay. Yeah, I can take both of those questions. So the first one, OpenACC, correct, our compiler does not support that out of the box. We have some ongoing support through GCC. We also have created a GPU Fort as a conversion tool to take OpenACC code, convert it to HIP, and then enable you to support the ISO-C binding methodology. So it imports it as a module into your Fortran code. We've seen some great performance using that methodology. And there's some more work going on with the HPE compiler will support OpenACC with the AMD GPUs. The second question was desktop support. So we actually, with ROCm 5.0, it's coming out next week. And it sort of worked earlier, but the Navi 21 series, so this is the W6800, it's a Workstation Pro version. It is fully qualified with the libraries and everything on ROCm on Linux. So that gives you a desktop solution. It has some great FP32 performance, and then supports all the same libraries and components.
Thanks.
Yeah.
Hi, thanks for the talk. I also have a question regarding the software stack ROCm. So you mentioned it's already supported in EasyBuild, and that's indeed true. But that was quite a bit of a puzzle to get together, because you have ROCm and there's all bits and pieces and libraries that fit together, and you have to install them in the right order. And at least until recently, we had quite a bit of trouble in making it behave. Let's say install in a specific prefix, and there were lots of assumptions there. So there have been lots of improvements there. That's very clear. But I was wondering if you can comment on what type of packaging issues you have been working on in the past, what's been solved already, and also if there's things you're still working on that will further improve the situation.
Yeah, for sure. We've heard lots of complaints about the packaging the last few years, and it has migrated towards a more usable infrastructure. So last year, even the year before, we tried to enable the multi-version install, and this was just supporting it through the standard Linux packages. But that became very complicated. With the 5.0 release, we've again sort of cleaned up all the packages, the subcomponents, how they're tied together, and supporting that as a method. Even the CMake environment, like for building from scratch, has been painful. So trying to improve that, improve the spec libraries, and then also the spec recipes, and then also improve, like now we need to get to the EasyBuild and make sure that everything stays aligned as we move forward. But our whole goal is to really make it seamless, right? So put everything together into a nice environment that makes sense between all the modules, because they were developed by different teams with different priorities, and like you said, different prefixes just get filtered through. And so it's getting better. 5.0 should have quite a few improvements in that sense.
Mm-hmm. And as you mentioned, what's supported currently in EasyBuild has mostly been done by contributors. Yes. Do you have plans to actively help out there with, first of all, maintaining what we have currently and expanding that, and also helping out, I guess, with the actual applications on top? Because I don't think we've gotten to the point where we actually have, let's say, a TensorFlow or a PyTorch on ROCm already working in EasyBuild, and it's not clear how much work that would be. But is that something you plan to help with, or would that require some kind of contractual obligations like there are on the US systems, for example?
Yeah, I would say we don't have a specific plan. We're definitely aware of the ask and sort of assessing it to see how we can enable our customers. I know a lot of the European centers are looking at having that support. So yeah, maybe just ping me offline and we can discuss in more detail.
Yeah, definitely up for that. That makes sense. Thanks.
Yeah. Is there any other questions? Someone has to give Michael a hardware question.
Looks like Michael has another question, maybe. Michael, or is that?
Oh,
yeah.
Sorry, I wasn't able to unmute me. Well, I have 2 more questions, so as we have some time. The first one is that I didn't see singularity in the app stack. So I know that you guys have some kind of support similar to what there is for NVIDIA, one flag at least ROCm. And the other questions, it's the point of view of development. What tools for debugging you guys have right now, and if there is something planned for the future in relation to debugger for ROCm and in GPU applications?
Yeah, for sure. So the first question, let's start with the ROCm debugger. So ROCgdb is our debugger. We've upstreamed most of the support. We're stuck on a few dwarf changes that need to go through the whole upstream process before all of it can be upstreamed. But that allows you to use GDB as you're normally familiar with, either through the command line or integrate it into an IDE. You can step through your code as well as jump into the kernel code on the GPU. There's a couple of good demos from the Linux Plumbers Conference that supports HIP and OpenMP. So I invite this, I think it was from September or October. There's a great demo there on the GDB. And the first question, Singularity, was so Docker containers are supported natively on Infinity Hub, but the Singularity instructions are there as well. So as part of that OCI framework, it just works. And we did spend some time with Singularity, let's say 2-3 years ago, to make sure that the flags were set up correctly for AMD GPU hardware.
Okay, thank you. Just a complementary question about that. Also, besides debugger, in relation to tools for profiling trace applications, I know AMD has a good tool for CPU, but it's not integrated with. There is no support for the GPUs right now.
Yeah, so actually, MicroProf or MuProf, depends on the name. It's the latest release. I think it came out last week, 3.5. It has the ROCprof integration into it. So you can check the documentation. It shows how to do that and add the tracing together. So that's the first step of sort of merging some of that functionality.
Oh, great news! Thank you.
Yeah, and the thing that I would like to add is that ROCprof is not only a command line interface, but it's more like a library or framework for performance analysis on our GPUs. So you can use the library interface to actually build your own performance tool on top of that, and that's what some of the community is doing right now. So, for instance, HPC Toolkit, I believe, is already working rather well on top of ROCprof, using that library to get performance data out of the GPU and present it as part of the general HPC Toolkit flow. And there's also projects with respect to Liquid, for instance, which is coming from Erlangen University in Germany. We are actively engaged with these guys to help them also support AMD GPUs. And I believe Scalaska is also looking at ROCprof at the moment and use that as kind of a data collection backend. So, there's MicroProf, but there's also community engagement around ROCprof to get performance tools for our GPUs.
Thank you very much.
I also have a small follow-up question, and maybe it was mentioned in the slides and then I missed it. But is there somewhere in the AMD documentation or maybe on GitHub, I'm not sure, an overview of all the libraries involved in ROCm and the stuff on top, like these profiling libraries or like things like custom Bliss fork and things like this, like a single page that lists them all, where you can click through for more details on each of these libraries, where they fit in the software stack?
Yeah, I would say our documentation is continually improving. All the documentation is public. We have AMD ROCmdocs.amd.com, I believe, is the current hosted site. and it's going under a refresh that it's hard to say if it'll land in this quarter or next. But yeah, definitely trying to make that a whole easier process to understand how the pieces fit together, as well as description of the documentation or of the modules. But everything is public. It's very scattered right now, and so we're trying to collect it into a nicer interface.
And the AMD, well, I think it's AMD user forum meetings that you mentioned. We actually, maybe it was you or Michael or some other people that were involved. We had a bit of a back and forth there. At some point, there were some plans to have an EasyBuild presentation there as well. But that sort of didn't happen because an NDA was required to join those meetings, because I guess AMD engineers were joining in as well. Is that still the case to join those user forum meetings, or?
That's a good question. I don't know. Michael, do you know?
Yeah, I guess the NDA part is just because so that people can, don't have to be that precautious when they talk about things.
Yeah.
But there will be more instances of the HPC user forum coming, and watch out for an invite. I don't know if there's a mailing list or something where you would have to register to get those news. But if you're interested, just drop us a note, and we'll make sure that you get the newsletter and the announcement for the next one.
Okay. Yeah, I mean, we could probably get an NDA in place because we have AMD systems and things like that. So in some sense, we are an AMD customer as well. But it's just a hassle to get through. And if we can get into a meeting that's maybe a bit more open, that's also maybe a bit more worth of our time to contribute to and to talk at. So, okay, but I'll contact you on this as well. Maybe you can see an opening there somewhere.
For sure.
Okay, do we have any other questions? Yes. I see Paul has a question.
Hi.
Yes, hello.
Can you hear me? Okay. So I was interested in how far is the Zipify tool in transforming CUDA code in terms of, for example, warp intrinsic instructions and that kind of advanced stuff. Does this work out already, or is it planned for the future?
So the Zipify does not work at the low level sort of kernel component. It's more at the CUDA level. So if you're doing like CUDA memcopy, CUDA launch kernel, it's at that layer. So if the kernel itself was written with any kind of intrinsic specific to NVIDIA, so like more like PTX or assembly, it doesn't convert that.
Yeah, the other thing that you typically need to watch out for is the warp size, right? Which for NVIDIA GPUs is 32. For us, the wavefront size is 64. And so if you have 32 as a magic constant in your kernel invocation, then that's another thing where you have to pay attention to move that over to be 64 for our GPUs. So there are, a bunch of things that the tool can't handle. It'll take you like 97% of the way. But then low-level code or even inline PDX, that's something where you would have to port that kernel yourself.
Okay, I see no other questions, so I guess we can wrap up. There's one thing I would like to do, so I'll quickly take over screen share here, because there's actually a related talk that's coming up at FOSDEM quite soon. So I hope the screen share is working. Is this showing the FOSDEM page? Yeah. So during the FOSDEM weekend, 5th and 6th of February, there's also a talk on AMD GPUs at the HPC dev room. This is done by Georgios, who's working on the Lumi team. So I guess this would also be interesting for the people here. So he's giving a view on the activities with AMD GPUs in the Lumi project. So definitely take a look at that as well. It's a pre-recorded video, but Georgios will be around during the time mentioned here in the schedule. So it's a Sunday for live Q&A as well. So this may be interesting. I'll share the link to that also in the EasyBuild Slack. And with that, I guess we can wrap up here. Thanks again, Michael and Derek.
Thank you.
Yeah, thank you.
All right. You'll take care.
Bye-bye.
Okay.